I'd like to introduce Dr. Phil Schoch. He is a senior material scientist within the chemical engineering group at Plug. He currently serves as the Fuel Cell Modeling Center of Excellence lead, focused on the development and implementation of fuel cell stack and system multiphysics models. Phil also lends his expertise in lab and pilot scale experimentation, surface science, membrane separations, and adsorption to ongoing efforts in humidifiers, coatings, and air filters. Phil holds a BS Chemical Engineering from Purdue University, MS and PhD from North Carolina State University. Phil's graduate work and expertise is primarily in soft matter physics, polymer chemistry, coatings, microstructured surfaces, and interfacial phenomena. Please welcome Phil. This is it, right?
Yeah.
All right. It's all yours.
Thank you. Thanks, Jake. And I'm glad to be here. This is actually going to be my first fuel cell talk that I've given outside of the company. I'm relatively new to fuel cells. I joined Plug last year. And actually, it's about the same time we became engaged with Gamma Technologies. So my talk today, I thought, okay, well, I want to talk about what Plug is trying to do with Gamma. What are we engaged about? Why are we motivated to work together? Why do we find GT Suite a compelling product to use? But also take a step into a realm that I'm passionate about, which is really connecting learnings from our most fundamental scales to system level. So you can make decisions from fundamental science all the way up to more engineering and business decision based things. This is something I've been passionate about since grad school, all the way through previous jobs and now at Plug. So I hope you enjoy this discussion. First, I gotta start with Plug is really ambitious. We're trying to do a lot of things very quickly. Our history has been in material handling systems, warehouse vehicles, so that's our GenDrive line of systems. But two big lines that are part of the future of the company is this ProGen line that's aimed at light duty to heavy duty transportation, as well as a GenSure technology that's focused on electricity production for data centers to telecom, backup power, all those sorts of things. So it's quite an array of applications that we're seeking now. But at the core of each of these is a fuel cell. That's what binds all of these technologies together. And so that's what I'm really going to try to focus on here. With the range of applications that we're seeking, we're also looking, or I'm part of who's looking to innovate our development cycle. So a classic V model that you might think of takes market research, seeking new potential spaces for applications and products, flows those down into potential system requirements, subsystem requirements, component requirements, and finally a detailed design. And then emerging out of that, component validation, subsystem validation, system validation, and ultimately to release. But we always want to connect the right-hand side of the page to the left-hand side of the page. And traditionally, that's experiential based. But in a more modern set, we really want to drive that connection using models. We want to be able to take our field experience, which is generally in the form of data. What Plug doesn't lack is data. We collect data on everything. All of our warehouse vehicles, we're constantly getting data. When they hook up to a hydrogen dispenser, we get a lot of run data. We know what they've been doing, how they've been doing it in a whole lot of ways. But if you don't have good models, you don't have a great way to connect the right side of the page to the left side of the page. So not only are we trying to innovate how we do the downflow from a market perspective to a component perspective, but also how we come back up the other side. And this really brings us to why we have become engaged with GT, with Gamma Technologies and using GT Suite. I have a lot of prior experience in this sort of stuff too, but fuel cell systems and vehicle systems is something relatively new to me, but the underpinnings of it being multi-scale and multi-physics is common, is a commonality between my experience and what this delivers. And I think it's especially valuable to our engineering team because it allows a lot of different engineering disciplines to exist on one page. I'm a chemical engineer. We have electrical engineers, we have mechanical engineers, you've got systems engineers, you've got you've named the type of engineer, maybe not civil, but we've got it, and we need to get them talking. And one of those ways is through models sitting on one page. It's a great unifier of an engineering organization. The other thing that I've been really passionate about in previous work and at this job is how do we get design modeling and experimentation to work cohesively? And what drives those connections? And I tend to break it down by scale. We ultimately want to deliver a product. We want to deliver a system. But all of what makes up a system is at other length scales, is at other principal scales, and how you're going to validate those and test those is scale dependent. And because we have different scale dependent testing, we also have different scale dependent phenomena. And so building up an overall system architecture relies on consistent methodologies from your most fundamental length scale to your largest length scale. And we've got a variety of goals that we're trying to achieve by taking this approach, but a lot of what we saw GT as being particularly useful for initially was basically from the stack component level and above. But the rest of this talk is really going to focus on how I've been taking steps into the cell and subcell level. The most principal aspect of a fuel cell is an MEA. We drive everything from the MEA level, and actually the overall plate size that you have and what conditions you have locally drive a lot of things relating to longevity of that MEA and what localized performance you can get and overall system efficiency. And that's really all driven by the bottom of the pyramid here. So with that, we started stepping into what can GT Suite do today, what's kind of easily accessible when we want to start discretizing the overall MEA area in our systems. And one of those things was this nice little widget that's built in where we can break up our overall flow field design and make custom connectivity. Most plate designs are not perfectly countercurrent or co-current. You always have some manifolding that makes certain sections cross-flow or counterflow or co-flow. But how that gets discretized in your model will change the way you connect your fundamental level results up to your system behavior. And we found that this was a pretty nice tool. It's not really intended maybe for system level modeling as it does extend model execution times, but it can be really useful for connecting to fundamental level testing. But we actually wanted something that could do a step further than this. And I had seen a vignette from actually Jake on how we could use a 3D 1D approach using the GEM 3D tool. And that would allow us to break the fundamental fuel cell stack module in GT into its sort of component domains. So we have MEA components, these electrical connections where actually the electrochemical reactions take place. Then we have MEA thermal masses, we have cathode channels, we have bipolar plates, we've got coolant channels, and anode channels. And so by breaking this apart, we can express each nodule is a 1D representation of a specific area, but the connectivity makes it essentially two-dimensional, and the way that they're connected together expresses thickness as well. So not only are you flowing across an area, you're actually expressing how things are connected vertically. So you actually get sort of a 3D connectivity to this. The other thing that was really interesting is it connects well with our very CAD-driven engineering design basis. So we can take our direct CAD files of how we actually go and construct our fuel cell stacks, and then we can extract out all of the negative space, all the flow volume, all of where, let's say, the magic happens in a fuel cell. And so I'm representing a cartoon representation, but if you actually did this, you'll see the detailed flow channels for your cathode, anode, and superimposed on your MEA area. And what you might get is certain areas that you want to discretize, and how you want to do that is going to be a function of what your flow area really looks like. In this case, we have sort of a mismatch between the serpentine pathway. And so we could make a whole lot of lists. I'm not going to make n number of options that you could have in your discretization, but two ones jump out at you really quickly. You can discretize by your larger area. In this case, our cathode loop. That's well represented by the widget as it was today. The other one that you can see is not well represented is our anode pathway. In the anode path, you actually get a significant number of sections that are not accurately being modeled as either co-flow, counterflow, or cross-flow. There's sort of a mix between. You can see, especially on the left side of the anode flow path, you see a U-bend, but then you have a return straight path. So we're going to get some approximation in that tool that may or may not be close enough. The other thing to consider is what area size. The overall plate size is about 230 centimeters squared, so each of these ends up being about 40 centimeters squared. That doesn't actually connect well to our smallest levels of testing. Our small cell tests tend to be around 25 centimeters squared, so this would be a little bit big for that domain size. And then at differential cell conditions, we tend to test really at 5 centimeters squared. So this would again be a little bit large for that. So if we wanted to pursue a fully customized route, we can actually break this up into 5 centimeters squared sections and actually represent between localized conditions in our flow pathing with how we might be doing differential cell testing, doing accelerated stress tests, doing degradation, and pulling out information for degradation modeling, et cetera. But through this pathway, I'll show you, we were able to achieve a sort of a fully customized discretization. And so this is what it ends up looking like. And I may have had to do a little bit of work to achieve this, but suffice to say, the GEM3D tool did allow me to customize to these. This is, if you count them all, there's 45 discrete areas. The anode side, obviously, it's a one-to-one match. We can use one channel. We can map it to each MEA zone that I've made. On the left-hand side of the page, though, to get one cathode channel in each of these sections, we actually end up using 3 parallel, if you stretch them out, 3 parallel cathode channels. And in these, we're better representing locally what are the conditions at any given point across the entire MEA area. Not only do we want to see this from beginning of life, but also to end of life, because those conditions are going to shift as different regions age differently from one another. Aging does not occur uniformly across the entire fuel cell. So there's a lot of things that we want to be able to connect together across these length scales, but drive from experimental information at this sort of scale, at the 5 centimeters squared scale. And ultimately, what does this end up looking like? The cartoon representation is up here. You can see roughly what the superimposition of anode flow and cathode flow look like. A lot of what experimental methods would tend to do is take either cathode outlet and anode outlet, or a cathode inlet and anode outlet condition and run those conditions. But actually what you see is those conditions don't actually exist on any point of the fuel cell. There's always conversion taking place, and what this allows us to pull out is locally any of the conditions that we would want to have experimentation take a look at. And so this is another way we've brought back together modeling, experimentation, and ultimately design. So that's what we're really trying to drive through this set of work. Ultimately, this deep discretization method that's via CAD and the GEM3D tool allowed for this customization and allows us to then target specific conditions locally on the fuel cell. So with that, I'm just going to step back through this. We're really trying to innovate our approach because we're really trying to meet a whole lot of different demands for a lot of application spaces. But fundamentally at the core of it is the fuel cell. And so we wanted to take a step into how deep down the well can we go with GT Suite. We found really great, we've had a really great experience so far with stack integration, but we wanted to take a step into how far could we discretize as well. This recent work really found a lot of potential. The built-in widget makes things very clean and easy. The CAD and Gem 3D, 3D 1D approach allowed for an immense amount of customization and this connection back between model, experiment, design. Ultimately, though tedious, it really was quite a powerful tool set, and ultimately is allowing us to drive decisions of what ages our systems quickly, which drives our costs of ownership, and ultimately drives our design decisions around fuel cell versus hybrid system sizing. So hopefully you found that somewhat interesting, and I'm available for questions. Thanks. Sure.
You mentioned specifically how this could be relevant towards degradation mechanisms and maybe longer permanent aging mechanisms. Do you have any more specifics you can share about which particular mechanisms are of interest and maybe what the time scale of that is?
Yeah, so locally, I'll say locally across the fuel cell, flooding conditions vary quite significantly. And so localized starvation mechanisms would occur differently across the entire fuel cell. They tend to also relate to system demands and how startup and shutdown conditions relate. So there's actually, I've actually got to go the other way and take a system level view down back to this level model. And I'm kind of excited about that work. That's work that's I'm just getting going now. I started out thinking, okay, I'm just going to connect the small scale to large scale, but I actually have to also go the other way and bring these startup and shutdown questions where you're either cold start or have other reasons that you might have a flooding condition that may occur, and what that might do at a local level inside the fuel cell. That's as much as I can say in that space.
All right. Well, thank you again.
Thank you.
Good presentation. All right, I hope you all enjoyed this split session. Please enjoy lunch.